Largest rectangle containing only ones. Largest rectangle. So you could build a height map and monotonic stack it. That's kind of annoying, but I guess you do that, right? So do I have to worry about 1D? No, I don't think so. Let's see. Map. Int row for row in A. Okay. Let's see what this comes up with. This should now have it be ascending. Great. Okay. And then from here you can say how far up is everything, and then you build a monotonic stack. I guess I could just do this right here. There's no real reason not to. So MSF is equal to, well, that's not relevant. Stack is that. Is it all working? Okay, that's working. This seems to be working. Great. Hi. Good boy. Let's see, stack is that. For J in range M, I could even just do it there, I guess. Right, I could just have right here. Let's see, so for every J, you're gonna wanna go back. Do I care about the, what do I need for the stack? I need how far back it is and what the height is, right? I don't think it's good enough to just have the number. So it's going to be something, something, stack dot append, J, A at J. So it's the height. So like when you're here, you would say 0, 1, 2, append index 3, height of 2. Do I care about this? What's the point of this? Yeah. This is kind of a nice warm-up. It's like an implementation heavy problem that I know exactly what to do. Okay, and then there's going to be something at the end that's like while stack. This is going to be everything at the end that you're able to, yeah, I think it's fine. That you're able to pop. So ideally, if you're at this row, you're saying all the rectangles ending at row 2. There would probably be like the convexity of it would be this as a corner and this as a corner. So you'd say while stack J and I guess height are equal to stack dot pop, and then you'd say MSF equals max MSF M minus J times height. And then that's going to be very similar to what this looks like. So while stack and while the height is greater. So stack at -1 at 1 is greater than or equal to, right? Yeah. The current height. I also kind of want like the index because that's what's going to go backwards. I need to keep track of that. So let's see, while that's greater than or equal to the height, if you're here, you're saying try going back until you get to here. So h1 index 1 is equal to stack.pop, except I think it would be index 1 and h1. MSF is equal to something, index equals index 1. MSF is going to be, you went backwards from J to there, and you're including J. So max MSF J plus 1 minus index 1 times height. And that might just be it. That's not just it. Okay, list an int. A.j and j while stack and stack at -1 at 1. Not supported between instances of, so stack at -1 at 1 is a list. Oh, I say A at J. That's a really weird thing to write. I assume this should just be H. Okay, perfect. This should work. No, it doesn't work because I'm not starting at index 0. If I and A at I at J. All right, well, let's see if there's a corner case. There is. So what happened here, there's probably some 0 thing I need to account for. Yeah, that makes sense. So let's see, H is going to be 0. So this will say, while there's a stack and anything on the stack, I don't think it's times H. I think it's times H1. You're saying while there's anything of greater height. So like if this were a 1 and this were a 1, you would be saying when you're here, you just blocked off this 6 wide, and you need to account for that. J plus 1, and now this is exclusive. All right, looks good, I guess. Nice. Okay, 8 minutes. That's pretty good for a kind of implementation heavy problem. Or at least like monotonic stack stuff like that is like not the easiest. Get rid of... Is this okay to keep? I think this one's fine. Yeah. Segment tree beats, I think that's fine. Let's see what we got. Weekly. Let's see. I think I did these two, right? If I look at this, this sounds right. Okay, I did this. This is the same one. Largest even number. I think I did this. I did. So those are done. I think this was the one that just happened. So I'll just start this. Looks good. maximum bitwise and after something. So maybe that's like a counts for monotonicity. When a string S consisting only of lowercase English letters, a prefix of S is called residue. Call the residue if the number of distinct characters in the prefix is equal to the length of the prefix %3. The number of distinct characters. Return the count of residue prefixes in S. Okay, that seems like really straightforward. I'll just say that is set for I in range N. Set dot add S set I res plus equals length of set is equal to I %3, but it's gonna be I plus 1 %3. Man, someone's car is really going off. 212, 212. I did not read that very closely. Number of centered subarrays. You're given an integer array nums. A subarray of nums is centered if the sum of its elements is equal to at least one element within that same subarray. The sum of its elements is equal to at least one element within that same subarray. Return the number of centered subarrays. Well, that necessarily means everything that's not that one element is equal to 0. So I think you're looking for the you're looking for the number of subarrays where everything but one element sums to 0, right? So I think you could say what subarrays sum to exactly 0. Where are their bounds? And then for every index, look at to the left and the right, how many subarrays begin and end exactly right there that are equal to 0. So here you'd say this is equal to 0. So therefore, this has at least one element within the same. The sum of its elements is equal to at least one element within that same subarray. If the sum was negative, that's exactly symmetric with it being positive. So it's the exact same case. If the sum is 0, you can just include something. No, I don't think that works. Because if you had like 1, 5, -1, you would say this does work. Well, how many? Oh, it's 500, so you just try every subarray. Right? Okay. For L in range N, for R in range L to N, I think I'll say set equal, not set. Cur is 0, that's the current count. And then, yeah, you just have a set. Set dot add A at R. Cur plus equals A at R. Res plus equals cur in set. Five, 2. Nice. Count Caesar cipher pairs. You're given an array of words of n strings. Each string has a length of m and contains only lowercase English letters. Two strings S and T are similar if we can apply the following operation a number of times. Turn an integer denoting the number of such pairs. Okay. Choose either S or T. Replace every letter in the chosen string with the next letter in the alphabet cyclically. Count the number of pairs of indices. What? Two strings are similar if we apply the following operation any number of times. Oh, I see. I see. Okay. So you're not given 2 words. You're given a bunch of words, and we need to know. Okay, well, you could just like anchor it all so that the first thing is 0 and then you go from there. Yeah, I'll do that. C is counter for W in A. Let's see. It's going to be something, let's see, offset is going to be equal to ord A at 0. And then I can say T is equal to tuple X minus offset for X in W. C at T plus equals 1. And then let's see the number of pairs of words. So it's going to be that times that minus 1. Return F times F minus 1 for F and C dot values, I think is what I want. Expected a character or W0. Zero, 2. This should be 1. So let's see, what are the tuples it comes up with? 0, 15, 3, 13, 3, 9, 8. Replace every letter in the chosen string with the next letter in the alphabet. Every letter in the chosen string. A, B, C, D, E, F. A, B, C, D, E, F. Oh, I see. I think I need to say, so it's ORed at this minus 97, if I'm not mistaken. Now A is anchored at 0. And then this will all be percent 26. But I forget how Python does it. I don't know how it handles percent negative, so I'll do that. That's 2. That's 4. Okay, now they've mapped to the same thing. I'm clearly off. So it's probably F times F minus 1 over 2, which is right. I'll just do that at the end, I guess. Okay, simple so far. Maximum bitwise and after increment operations. You're given an integer array nums and 2 integers k and m. You can perform most k operations. In one operation, you may choose any index I and increase nums at I by 1. Return an integer denoting the maximum possible bitwise and of any subset of size m after performing up to k operations optimally. I see. So you can add in at most k. You want the maximum bitwise and this seems like you might need to like start and say, can you obtain the largest bit? And then if you can you obtain the next largest bit and so on. So here you'd say like, what if we added, can we get to 8? Well, this can get to 8. And then we have that much left over. If you're trying to obtain a bit, what's the best possible way to do that? Of any subset of size m. That's okay. That makes it a lot more difficult. No, I don't think so. I think you're always going to take the maximum. And then if you can't obtain a bit, then everything doesn't get that bit anymore. And this is going to be like O of n log n, O of n log squared n. So you'd say, can I obtain 8? If this was like 11, the answer would be yes. And then you'd say, okay, having obtained 8, this is the lowest cost I can spend to do that. Now that's necessarily the best option. And then go from there. Can you obtain a 4-bit? So here you'd say, can I obtain an 8-bit? No. Here you could obtain an 8-bit. You'd say 8 and 4. No, you can't because m is 3. But if m was 2, you could. Maybe there's another test case. No, it doesn't matter. Yeah, you'd say, can I obtain an 8-bit? No, because these 3 things would need to be increased to at least 8. So then you'd say, okay, now I basically have 1, 2, 0, and 4. Can I obtain a 4-bit? Yes, because this is good. This only needs to go up by 2, and this needs to go up by 3. And then you'd say, can I obtain a 2-bit? Now we have 0, 0, and 0. 2 and 3, and we have only 1 more bit to spend. Okay, so it's like a greedy thing, I guess. So first things first, a.sort. Do I even want to do that? I think I just want to say take the top k. Well, k is 10 to the 9th. Wait, what the hell does that represent? No, top m. Which is less than n, but I don't think that really matters. Well, no, it kind of does, because once you've selected the m that you need, those are the only characters. So you need to select your highest bit and then modify exactly those characters. But if you had more than m characters that get you your highest bit, then you still select all of them. So you do have progressively descending candidates, but you would immediately eliminate candidates that weren't selected. Okay, got to go soon, but let's see. So you'd say A contains only the candidates that currently work. Right? Find highest bit. Dang. That sucks. I mean, not really. I want to get on with it. But I feel like I'm making insanely good pace. I finished the first 3 questions in 8 minutes, so whatever. I think I'll probably stop streaming when my girlfriend gets here and then just continue these. I don't know. But okay, so get the highest bit. I don't even know if that's the right methodology. I don't think it's like you're selecting for the high. I think it's like you're narrowing candidates. So I'll just say, well, no, but the only way that you could have, if you were like M is 3 and I need 4 candidates, I have 4 candidates with like a 16-bit set, you already have 4. There's no way you're going to spend M to get 4. If you didn't have 4 and you needed to spend any M, then you would have just spent the M on exactly the 3 cheapest candidates. Yeah, okay. For x in A, if x and 1 to the bit. I think I'm just gonna say in y equals 1 to the bit. If x and y b dot append x, okay. You keep doing that. And then eventually you're going to get something that's like else, let's see. I don't think that's a great way to do it. If x and y b dot append to x, so how many already have this? You're just finding the earliest possible point where you can set this to have that bit set. So I almost want like a heap, honestly. Maybe not that. If x and y, b dot append x. Do I just go again? I don't think that's a good call. All right, I'm shutting the stream down. I'm gonna finish this off stream because I gotta go in 5 minutes anyway. See ya.